Globally, about 1.3 million people die each year from traffic crashes. More than 25 million people suffer permanent disability. Motorcyclists are the highest percentage of road deaths, with 61% of the national fatalities. However, in urban areas, such as the Greater Jakarta area, they account for 70% of the total fatalities. Other vulnerable road users, pedestrians and bicyclists, account for about 28% of the total road deaths on Indonesian roads, whereas four-wheeled automobiles, cars and trucks, constitute just 7% of road fatalities. High-income countries have shown a substantial reduction in road crash fatalities by an average of 10% over the last 2 decades. However, in most developing countries, including Indonesia, the situation is worsening. Without any action, the numbers will increase significantly. Moreover, there are notable differences in the way different road users are affected by road crashes. More than half of global road traffic deaths involve young adults between 15 and 44 years of age. 73% of all global road traffic fatalities are males. Vulnerable road users, pedestrians, bicyclists, and motorcyclists account for a much greater proportion of road traffic collisions in low-income and middle-income countries than in high-income countries. It is difficult to detail the magnitude of the problem of road crashes in Indonesia due to the large underreporting of crashes. According to police data, the number of deaths in 2010 was some 31,000. Other figures, derived by road safety professionals, suggest it may have been above 40,000 deaths. Motorcyclists are the highest percentage of road deaths, with 61% of the national fatalities. However, in urban areas such as the Greater Jakarta area, they account for 70% of the total fatalities. Working for improved motorcycle safety should be a key objective for road safety engineers in Indonesia. Indonesian data confirms international figures, which show that more than half of all global road deaths occur to people aged between 15 and 44 years. In Indonesia, some 77% of road fatalities are male, which is in line with global figures that show that the majority of fatalities in road crashes are male, whilst 23% of road fatalities are female. Crash data from toll roads in Indonesia is more comprehensive than from other roads at present. Single vehicle crashes, rollover, or loss of control crashes are the most common type of crash on both Indonesian toll roads and non-toll roads. The economic loss of road crashes is substantial. It can hold back economic development, and it can destroy the welfare of a family when a family member dies in a crash. Studies suggest that up to 63% of families affected by a road crash fatality lose their ability to maintain their economic standard. The road system consists of 3 key components: the road user, or human, the vehicle, and the road. Each of these components can contribute individually to crashes. However, it is more common for a crash to involve a complex interaction between these components. Many nations now have their own national road safety strategy to guide and direct national resources. These national strategies vary from nation to nation due to the differing national crash problems and the stage of national development. Most tend to be structured around 5 pillars, reflecting safe system thinking. Pillar 1, road safety management. Pillar 2, safer roads. Pillar 3, safer vehicles. Pillar 4, safer road users. Pillar 5, post-crash response. Improving road safety in Indonesia will involve safer road users, safer vehicles, and safer roads. You and your colleagues now have a vital role to play in developing safer roads for Indonesia. Many engineers in emerging countries such as Indonesia underestimate the importance of their work in reducing road crashes. Some of them think that crashes are totally due to the faults and mistakes of the road user. They believe that the only way to improve road safety is for police to be stricter and more effective with enforcement. However, they fail to realize that many of the human mistakes that are made on the roads are due to failings by an engineer, a drain that is unnecessarily close to the road, a length of misleading line marking that draws drivers and riders into head-on conflicts, an obscured or incorrect road sign, a lack of facilities to assist young pedestrians to cross a busy highway to get to school. This series of DVDs and the accompanying manuals will demonstrate through both theory and practical examples that engineers have a vital role to play in providing safer roads for all Indonesians. An intersection is defined as a place where 2 or more roads meet at grade. Intersections are particularly high-risk locations because different road users, trucks, buses, cars, pedestrians and motorcycles, are required to use the same space, and collisions are only avoided if they are separated in time. Intersections are the location of up to 50% of reported urban crashes and between 10 to 20% of reported rural crashes in most countries. This difference in percentage between urban and rural intersections is due to the greater number of intersections and also usually higher traffic volumes in urban areas. Higher traffic volumes equal greater exposure, which in turn leads to greater crash risk. Intersections can be categorized into one of 4 main groups: four-way or crossroad intersections, T intersections, Y intersections, multi-leg intersections. The main forms of control at intersections are road rules, relying on a priority rule to indicate right-of-way, priority road designated by give way or stop signs, roundabouts, traffic signals. Whether you are designing a new intersection or you are investigating an intersection that has become a black spot, the principles of intersection safety are the same. They are adequate sight distance. The 2 most important sight distances to consider for your intersection are approach sight distance. Every approaching driver or rider needs to be able to recognize and understand the priority that applies at the intersection. They must also be able to clearly see the path they should take through the intersection. ASD is the minimum sight distance which should be provided at an intersection. It is defined as the distance required for a driver or rider to perceive markings or hazards on a road surface approaching an intersection and to stop. Safe intersection sight distance. SISD is the minimum distance that should be provided on the major road at all intersections. It is measured along the carriageway from the approaching vehicle to the point of conflict. It provides sufficient distance for a driver or rider on the major road to see a vehicle on the minor intersecting road moving into a collision position, then to decelerate to a stop before reaching the collision point. Minimizing conflict points. A conflict point is a point within an intersection where the road space required by one line of traffic may be simultaneously required by another. The more conflict points in an intersection, the greater the risk of a crash. It is an important requirement for safe intersections that the number of conflict points be kept to a minimum. A crossroad has 32 conflict points. By closing one approach to the crossroad intersection and creating a T-junction, the number of conflict points drops to just 6. Converting a crossroad intersection to a roundabout then further reduces the number of conflict points to just 4. This does not mean that you must convert every intersection to a roundabout, or that you should convert all crossroads to T-junctions. But it does mean that you should give thought to all possible ways to reduce conflict points in your intersections. Reduce the relative speed between vehicles. Most engineers understand the threat of a head-on collision, but few appreciate the high impact speeds generated during right-angle collisions. Intersection crashes tend to yield very serious outcomes because intersections are the location of the most right-angle crashes. When these crashes occur at high speed, their severity is very high and fatalities are common. Give precedence to major movements. Drivers and riders expect the major road to be given precedent at an intersection. Separate conflicts in space and time. Traffic signals are a form of traffic control that separates conflicts within an intersection in time. By controlling which approach is able to enter the intersection at which time, potential conflicts can be eliminated, but only if drivers and riders comply with the traffic signals. Define and minimize conflict areas. Safety is maximized when the conflict area of an intersection is kept as small as practical. This can be achieved by providing only the area needed for the intersection, squaring up the intersecting roads, minimizing the number of lanes provided and marking these clearly. Define vehicle paths. Drivers and riders need guidance as they travel along a road. Lane lines are used for this purpose. When approaching an intersection, this becomes even more critical. The actual vehicle path definition depends on the type of intersection and the traffic control provided, but it is highly desirable to define each vehicle path clearly and positively. Control approach speeds. Drivers and riders should not be permitted to approach, enter, or pass through an intersection at a speed that is clearly unsafe for the conditions. This can be achieved by a combination of alignment, speed control, lane width, and traffic control. Provide clear indication of right-of-way. Safety is maximized at intersections when every driver or rider knows and complies with the road rules that apply to that intersection. Minimize roadside hazards. Roadside hazards are defined as any fixed object with a diameter of 100 millimeters or more located within the clear zone. Roadside hazards include power poles, street lighting columns, trees, rocks, cuttings, buildings, bus shelters, deep drains, and undrivable side slopes. Provide for all vehicular and non-vehicular traffic. Many intersections quickly become centres of activity soon after they are opened. People congregate there to catch local buses, taxis, BJEX or OJEX. Encroachment should not be tolerated, and a determined effort should be made by the local authorities to keep major intersections free of encroachment. Engineers have a vital role to play in preventing encroachment. Make plans to accommodate waiting passengers in shelters located away from the intersection. Provide indented laybys for the buses to pull into and pick up or set down passengers. Provide wide footpaths with areas at the rear for stalls and food carts to operate without causing pedestrians to walk on the road. Simplify the driving task. This simply means to make the intersection as simple to use as possible. Keep it open, ensure the line marking directs drivers and riders clearly, and that signs and other traffic control items are conspicuous, clear, and correct. Minimize road user delay. Do your best to minimize delays to the road users at your intersection. If drivers and riders accept the time that it takes to safely negotiate your intersection, they are less likely to abuse the traffic control there. Indonesia has many Y-junctions. They are a very simple form of intersection that evolved when traffic volumes were much lower than today. However, as traffic volumes have increased, these Y-junctions have become high-risk locations because they do not satisfy the basic principles of safe intersections. They have large conflict areas. They have high relative impact speeds. They lack clear priority. For all of these reasons, no more Y-junctions should be built. Existing Y-junctions should be examined and a national program established to eradicate them, or at least to provide positive traffic control at them. To eliminate Y-junctions, or to reduce the risk at a Y-junction, you have several options. Close one of the approaches, thus eliminating the intersection. Convert the Y-junction to a T-junction by bringing the minor leg into the major road at a right angle. If the Y-junction is in an urban area, consider installing a set of traffic signals. This will separate the opposing traffic. This will also assist pedestrians to cross at these locations. A roundabout may be suitable to replace the Y-junction. The first level of traffic control at an intersection is to install a stop or a give-way sign to control the traffic. The sign should be located where it can be clearly seen by approaching drivers and riders. It should be on the minor leg of the intersection. It should have a line marking on the side road to indicate to drivers and riders where to stop or give way. A roundabout is a particular type of intersection control that includes a central island within the intersection, around which all traffic is required to travel in a clockwise direction. Drivers and riders are required by the road rules to give way to the traffic that is already on the roundabout before entering. Roundabouts are a proven safe form of intersection control because they simplify the decision-making process for drivers and riders, reduce the relative vehicle speeds of conflicting movements, reduce the number of conflict points from 32 to just 4 as opposed to an intersection. Basic components of a roundabout. A safe roundabout has suitable deflection on each approach, splitter islands, either physical or painted on each approach, a circulating carriageway that is wide enough for the number of circulating lanes, a conspicuous central island. Locations where roundabouts are best suited. International experience has shown that roundabouts are best suited to the following locations: at stop or give-way controlled intersections that are suffering undue delays due to the minor approaches, at intersections with high volumes of right-turning traffic, at rural crossroad intersections that have a high-speed crash problem, at intersections where the major road takes a turn through the intersection, at intersections with more than 4 approach legs, locations where roundabouts are not suited. A roundabout will generally not be a suitable countermeasure if your black spot intersection is located at one of the following types of locations: where a suitable safe geometric design cannot be achieved, where traffic flows on the approaches are unbalanced, where a major road intersects a minor road and the delays on the major road would be unacceptable. How can you improve safety at an existing roundabout? If you have a black spot that happens to be a roundabout, there are a number of things you can do. It will usually be too expensive to alter the geometry, so you need to look at the signage and markings to make changes. Inspect the site daytime and nighttime, looking at what the drivers, riders, and pedestrians are doing. Design considerations for a safe new roundabout. Once you have decided on a roundabout for your intersection, there are some essential design matters to take into account. Number of lanes. Only provide the minimum number of traffic lanes necessary for capacity. Crash rates increase when more lanes are used. Deflection. It is essential to minimize the relative approach speeds and also to create shallow angles of impact. Design the roundabout for all vehicles to give way to the right. Never consider any situation that permits entering traffic to take priority. Street lighting. Essential and preferably in the middle of the central island. Strong line marking, especially the give-way line. Signage must be correct. Regulatory signs at the holding line, advanced direction signs on the main road approaches, and if high approach speeds are involved, also install advanced warning signs. Roundabouts are the safest form of intersection control provided they satisfy these basic design elements. Traffic signals provide control by separating conflicting movements in time. Vehicle-actuated traffic signals offer the best way to minimize delays for road users. Vehicle-actuated traffic signals respond to the presence of vehicles on each approach. If there are no vehicles on that approach, the signal controller skips to the approaches where demand is greatest. Such vehicle-actuated signals can accommodate pedestrian push buttons, allowing pedestrians to call up their phase at the earliest possible time in the cycle. The following are some key issues regarding traffic signals. Always use vehicle-actuated traffic signals. Provide a fully controlled right turn, if that right turn has to cross 3 or more traffic lanes. Ensure your signals can be clearly seen on each approach from at least 100 meters in advance. Always mark a stop line adjacent to the primary signal pedestal. Always mark each traffic lane. Use lane designation arrows to show drivers and riders in which direction they must travel through the intersection. Where a right turn lane is to be provided, ensure that this is indented into the median. Treating intersection crashes should be one of your highest priorities as a road safety engineer. Here are some examples of common intersection crash problems in Indonesia. Cross-traffic crashes. Cross-traffic crashes are crashes which take place at crossroads and will usually be either overshoot or restart crashes. Overshoot crashes are where the driver or rider of the vehicle on the minor road is unaware of the intersection and drives into it without slowing. If this happens at the time a second vehicle is driving through the intersection, on the intersecting road, a right-angle crash will occur. The most appropriate countermeasure for overshoot crashes is to improve the conspicuity of the intersection. You can do this in a number of ways, including trimming obstructing foliage, repainting center lines and holding lines, advanced warning signs, advanced direction signs, lighting, duplicating the stop and give way sign, installing a splitter island on the approach. On the other hand, restart crashes occur when a driver or rider slows and even stops at the give way or stop sign, but then selects an inadequate gap in the traffic. You might ask why a driver or rider would select such an inadequate gap. Are sight lines obstructed? Are major road speeds excessive? Or are major road volumes so high that entering drivers feel pressured to take small gaps? Right turn against crashes. Right turn against crashes are a problem at signalised intersections. Efforts to reduce the incidence and severity of right turn against crashes mainly involve the use of turn phases for the relevant movements. Pedestrian crashes. A substantial proportion of pedestrian casualty crashes occur at intersections. At traffic signals, pedestrians can be assisted through fully controlled right turn phases or split phase arrangements to separate the vehicle and pedestrian movements in time. Rear end crashes. Rear end crashes can occur anywhere on the road network. However, they are most likely at intersections where a driver or rider makes a decision to stop and a following driver or rider fails to respond in time. Do your best to make all approaching drivers and riders aware of the presence of the intersection. We can never be sure just where, or when, or why a vehicle will run off the road. It may be due to many reasons: human error, vehicle defect, traffic issues, or the road. We know run-off road crashes are a serious problem for Indonesia, despite reliable crash data being difficult to obtain. This problem is likely to worsen in the near future as speeds increase with more duplicated highways, more tollways, more urban flyovers, and localized traffic capacity improvements. A roadside hazard can be defined as any fixed object with a diameter greater than 100 millimeters that is located on the roadside within the clear zone. The clear zone is an area alongside a road which should be kept free of hazards. The width of a clear zone depends on the traffic speed and volume, as well as roadside geometry. The roadside hazard management strategy has 5 steps. Manage the road and traffic to keep vehicles on the road. Remove the hazard. Relocate the hazard to a safer location. Alter the hazard to reduce impact severity. Install safety barrier to shield the hazard. As you work through the roadside hazard management strategy, you will reach a time when you ask, what can best be done to treat a hazard? Many engineers immediately jump to installing safety barriers. But these are not always the best or safest solution. Explore all options and only agree to a barrier if it is clearly the only practical option. Safety barriers are the last resort in roadside hazard management. There are many locations where a barrier is the only option available to improve safety. There are 3 groups of barrier, classified by their rigidity into the following types: rigid, concrete barriers; semi-rigid, steel W-beam guard fence; flexible, wire rope safety barriers. As you manage your roadside hazard management program, remember the importance of maintenance in road safety. All road devices must be maintained when in use. The maintenance crews responsible for this need training about the proper installation and maintenance of barriers and other roadside hazard treatments. Drivers and riders receive about 90% of their necessary driving and riding information visually. The 2 most common devices that engineers use to provide them with this information are signs, line markings. Both are so commonly used on the roads that they are often taken for granted. This has led to some signs and line markings being used incorrectly, inefficiently, or unsafely. Start by remembering the 6 C's of good signage in your road safety engineering work. If your sign or line marking meets all the 6 C's of good practice, then it will be sure to assist drivers and riders to safely use the road. The 6 C's require signs and line markings to be conspicuous, clear, comprehensible, credible, Consistent. Correct. The use of standard signs and markings on all the roads of Indonesia is to be strongly encouraged. Drivers and riders react more quickly and more correctly to standard signs than they do to non-standard signs. Quicker and more accurate decision-making is one of the key ingredients of safer traffic. There are two main signing conventions in the world: American and European. Indonesia tends to follow the US sign convention for its warning signs and the European convention for its regulatory signs. This is perfectly acceptable. The most important aspect of this is for engineers across Indonesia to consistently use the correct sign for the task. Drivers and riders demand consistent information, and this is one thing that engineers should work towards. Regulatory signs. Regulatory signs inform road users of traffic laws. They are enforceable and must be obeyed. For this reason, every sign used must comply with the Indonesian road rules. Warning signs. Warning signs are used to warn road users of potentially hazardous conditions on or adjacent to the road. In Indonesia, they are black on yellow diamond-shaped signs. In addition to satisfying the 6 C's of good signage, a warning sign should be specific. It must warn the approaching driver or rider about the hazard ahead. Warning signs exist in 4 series. Alignment series. These are signs warning of a sharp curve or series of curves. The advisory speed sign indicating the safe speed of a curve may be used below the sign. Intersection series. These give advanced warning of intersections where the road layout, sight distance, or other devices are inadequate to warn the driver or rider of the existence of the intersection. Pedestrian, bicyclist, animal series. These warn of locations where pedestrians, bicyclists, or animals may be expected on the road ahead. General warning series. Warning of issues such as structures, obstacles, rough surfaces, and other hazards ahead. Warning signs are usually permanent, but some may be used on a part-time basis to warn of intermittent hazards. Guide signs. These signs inform and advise road users about the direction and distance to destinations in the road system. They inform them of services or features of interest along the road and give instructions. Although not regulatory, these instructions should be obeyed. As a general rule, allow 2 seconds for any sign to be read. Allow 2 seconds travel time between sequential signs. Limit all direction signs to a maximum of 5 lines of information. Use only standard fonts. Always use reflective materials for the sign face. The minimum requirement for the lateral placement of a sign is for it to be clear of damage from passing traffic. But it should not be displaced laterally more than necessary, as it will lose prominence and lose effective reading time. Certain signs, in particular most regulatory signs, indicate by their location the point at which the corresponding control or regulation takes effect. Certain other signs, such as intersection direction signs, mark the point at which an intersection or other potential hazard occurs. There are 3 groups of pavement markings: longitudinal lines, transverse lines, pavement word or symbol markings. The real value of pavement markings is that they are placed on the road surface where the driver's or rider's eyes are fixed for most of the time. Separation lines. These are usually a 100mm wide broken line with stripes about 1/2 of the gap length. Barrier lines. These comprise a pair of 100mm lines, either double unbroken or unbroken and broken. Crossing or driving to the right of a barrier line is illegal. They are commonly used to prohibit overtaking on two-lane, two-way roads. Edge lines. These are solid 100mm lines located at the edge of the carriageway. They improve delineation for highways in both rural and urban areas. Markings at stop and give way signs. These are used at intersections and crossing points to indicate the place at which vehicles must stop in compliance with the traffic control. Pedestrian crossings, otherwise known as zebra crossings. Words and symbols can be applied to the road surface to convey a message, usually in advance of a decision point. For example, the X marking is generally used in advance of a rail level crossing. Remember that the visibility of pavement markings can be affected in a number of ways. Drivers and riders view pavement markings from low angles. A film of water on the road will reduce the reflective efficiency of line markings at night. Delineation is the term given to the provision of signs, line marking, and other traffic devices in order to guide drivers and riders, especially on substandard curves. Long-range delineation enables the driver or rider to plan their forward route, and thus it needs to be consistent and continuous. Delineation devices fall into two groups: pavement markings and roadside devices. Pavement markings. Pavement markings are usually applied using either paint or thermoplastic material. Because they are required to operate at day and night, they should be highly reflective. They also need to be skid resistant and durable. The message they convey must be clear and not lead to confusion. And since any given symbol may be visible for only a very short time, the message must be simple and clearly understood. Raised reflective pavement markers. Raised reflective pavement markers, or RRPMs, are small reflective devices that are glued to the road surface. Being raised slightly, they present a reflective face to oncoming traffic. RRPMs provide better nighttime delineation than painted center lines and edge lines, especially under wet weather conditions. Roadside devices. Guideposts and post-mounted delineators. Guideposts are lightweight posts typically located 1 meter from the edge of the road. In Indonesia, they need to withstand heat and humidity and heavy rainfall. Most importantly, they should not present a safety hazard to road users. The concrete posts used on many Indonesian roads are unsafe. It is preferable to use other materials, including plastic, timber, fiberglass, aluminium, or thin steel. Chevron alignment markers. These are single chevrons with highly contrasting black on yellow colors. The use of cams is restricted to those locations where drivers need additional strong delineation to guide them through curves which are substandard compared to the adjacent curves. The geometric design of roads is a detailed field that involves thinking in 3 dimensions within the natural terrain so that the needs of the road users are met safely. As a road safety engineer, you are not expected to be a road designer, and you are not expected to be an expert in geometric design standards. However, you are expected to take geometric design into consideration when addressing all aspects of road safety. Geometric design standards serve 3 main purposes. They help to maintain a degree of uniformity and consistency in road design. They help to ensure satisfactory road designs are produced, even in jurisdictions where there is little design experience. By avoiding excessive designs, they tend to ensure that scarce road funds are not misspent or wasted. There are 5 basic elements of geometric design that impact on safety: design speed, cross-section, including drains, medians, and sealed shoulders, sight distance, horizontal alignment, including superelevation, vertical alignment. The design speed is not the speed limit for a road. While the two should be close in value, there are many existing roads that have a design speed 10 or 20 kilometers an hour above the speed limit. This has usually been done for safety reasons, to build in a margin for error. However, many experienced road designers now challenge this theory because it leads to more expensive roads and it encourages some drivers or riders to exceed the speed limit. The cross-section of a road is a section of the road taken at right angles to the direction of the road. It includes shoulders, lanes, and medians. Ideally, all road cross-sections should include wide sealed shoulders, consistent and generous width lanes, and a wide central median. All drains should be underground, and there should be no roadside hazards within the clear zone. An important aim of road design is to ensure that the drivers and riders, while travelling at or below the design speed, are able to see potential road hazards in sufficient time to take avoiding action. Humans take time to react, and they need distance in which to take avoiding action. The faster they are travelling when they first see the hazard, the greater the stopping distance needed. This is where the concept of sight distance is vital in road safety. The most important sight distances for safety at intersections are approach sight distance, ASD, safe intersection sight distance, SISD. Approaching drivers and riders must be able to recognize the presence of an intersection and its layout and have time to react appropriately. Approaching drivers and riders should also be able to understand the priority that applies and clearly see their path through the intersection. This is where approach sight distance is necessary. It helps to reduce the risk of a driver or rider overshooting the intersection. Stopping sight distance is the distance required to enable an alert driver or rider to travel at the design speed on wet pavement and to perceive, react, and come to a stop before reaching a hazard on the road ahead. This distance is considered to be the minimum sight distance that should be available to a driver or rider. To improve safety at locations that have sight distances below the SSD, you have several options. Improve sight lines by reducing vertical curves. Increase sight lines across horizontal curves, sometimes by cutting back vegetation on the inside of the curve. Reduce the operating speeds with good speed restriction signs and police enforcement. Improve the skid resistance of the road pavement so that vehicles may stop in a shorter distance. Overtaking sight distance, or OSD, is the distance required for a driver or rider to safely overtake a slower vehicle without interfering with the speed of an oncoming vehicle. Overtaking sight distance is considered only on two-lane, two-way roads. On these roads, the overtaking of slower moving vehicles is only possible when there is a suitable gap in the oncoming traffic, accompanied by a sufficient sight distance and appropriate line marking. If you are investigating a location that has a history of head-on crashes, you should check that the OSD is met. If it is not, you have several options. Improve sight lines by reducing vertical curves. Increase sight lines across horizontal curves. Reduce the operating speeds with good speed restriction, signs, and police enforcement. Install no overtaking lines. Construct an overtaking lane. The horizontal alignment of a road is its alignment in the horizontal plane. The most significant factors to consider for safety in horizontal alignment are the radius of the horizontal curves and also the development of the super elevation that leads into and out of each curve. Larger radius curves generally provide greater sight distance. Drivers and riders are able to see through the curve and to make safe decisions earlier. However, this safety benefit can be lost if vegetation is allowed to grow beside the road and is allowed to cut off the sight lines. Shorter radius curves may restrict sight lines and usually restrict reasonable drivers and riders to low speeds. However, if unrealistically high speeds occur, it may be necessary to apply additional speed management. Operating speed design. Tendency of very slow-moving vehicles to track towards the center and the stability of those vehicles. Differences between inner and outer formation levels, and length available to implement the necessary super elevation. Super elevation is primarily needed for safety, but other factors such as comfort and appearance are also relevant. While super elevation is necessary for safety, you need to be careful that the super elevation provided is not excessive for the location. Some super elevation is good, but too much super elevation can have a negative effect on the location. It is not often that you will have the freedom to decide where to place an intersection. However, if and when you do, place the intersection where it offers the best level of safety for the road users. This will depend on horizontal alignment. If possible, place a crossroad intersection on a long straight section of road. This maximizes sight lines in both directions. Placing a T-junction on the outside of a curve is also good for safety. Drivers and riders are able to have a good sight distance in both directions. On the other hand, placing a T-junction on the inside of a horizontal curve can lead to serious sight restrictions, regardless of vertical geometry, causing vehicle entrance safety issues. Effective gradient. Generally, grade should be as flat as possible, consistent with economy and longitudinal drainage requirements. Flat grades permit all vehicles to operate at the same speed. Steeper grades produce variation in speeds between vehicles with varying power-to-weight ratios. Vertical curves. Steep vertical curves have a direct and strong impact on the speed of heavily loaded vehicles, such as trucks and buses. In Indonesia, a country with a history of heavily overloaded trucks, this can create dangerous situations. Steep uphill sections have been known to become the sites of rollback crashes, when trucks lose power and their brakes fail to prevent them from rolling backwards. Steep downhill sections have been the location of trucks losing their brakes due to overheating, or run-off road crashes due to excessive speed. Coordinating horizontal and vertical alignments. The horizontal and vertical alignments of a road should be coordinated to avoid inadequate stopping sight distance and broken back illusions on the curvature of bends. Road designers try to achieve this by making all points where horizontal and vertical curves change coincide with one another. Where this is not possible and the curves cannot be separated entirely, the vertical curve should be contained either wholly within or wholly outside the horizontal curves. Where curves are allowed to overlap, the resulting optical illusion may be damaging to the appearance of the road and may contribute to road crashes. Pedestrians are the single largest, as well as the most vulnerable, of all road user groups. In the event of a crash with a motor vehicle, the pedestrian is the most likely to be injured, often seriously. Unfortunately, pedestrians in Indonesia get little practical assistance on the roads. It would seem that the largest road user group is also the most disadvantaged. It is time for this to change. As a road safety engineer, you can make a positive difference for pedestrians by paying particular attention to their special safety needs. It is not possible to be sure how many pedestrians are killed or injured in road crashes each year in Indonesia due to unreliable crash data. It is known that in Western countries, pedestrians constitute 12 to 15% of road crash fatalities. In Indonesia, pedestrians comprise at least 15% of the known road toll. Do not restrict or obstruct pedestrians. Placing barriers, fences, and other obstructions to try to prevent pedestrians from using a route is a fruitless exercise. There are some exceptions. Fencing expressways to keep pedestrians off is one good example. Pedestrians will take the shortest path. Pedestrians will not walk out of their way to use a device simply because you have installed it for them. They will take the shortest path based on their perception of time, distance, and risk. Pedestrian devices must be placed on or close to the desire line for the pedestrians. Pedestrian facilities rely on driver and rider compliance. Installing a zebra crossing or a set of signals will not assist pedestrians unless drivers and riders comply with the rules. All pedestrians deserve your assistance. However, based on international crash data, there are 4 groups of pedestrians that are at greater risk than others when they use the road. The young, the elderly, the disabled, the impaired, intoxicated, and drug affected. Young pedestrians who are involved in road crashes tend to have them during daylight hours and generally on the trip to or from school. Some questions to ask yourself are: does the school gate open straight onto a busy road? Do the children need to cross the road, or is it an option to have them walk along the same side as the school? Are footpaths provided along the road? If so, are these continuous? Is there a crossing at the school? Is it well marked, and does it have regulatory signs? Controlling vehicle speeds overall is a positive way to assist young pedestrians, many of whom are too young to have developed the skills necessary to pick a safe gap in traffic. Pedestrian crashes involving the elderly tend to be more severe than crashes involving younger people. Some questions to ask yourself are footpaths smooth and continuous? Are curb ramps provided to help the elderly to step on and off footpaths? Is there a need for a pedestrian facility? If so, push-button signals offer the elderly the best and the most reassuring level of assistance. Road safety engineering is inclusive of people with sensory and physical disabilities. Some questions to ask yourself are the footpaths smooth and free of obstacles? Does a wheelchair user have access to a curb ramp to get on and off the footpath? Is the footpath clear of obstructions, and wide enough to accommodate wheelchair users, plus others? Is there a distinct boundary between the footpath and the road for visually impaired people to know when they have stepped off the footpath? If pedestrian-operated signals are provided, can a person in a wheelchair reach the button? If signals are provided, do they have audio-tactile devices that alert visually impaired people to the phasing of the signals? Intoxicated and impaired pedestrians are overrepresented in serious nighttime pedestrian crashes in Western countries. Less is known about this in Indonesia. Some questions to ask yourself are: is there adequate street lighting? Are drivers and riders given every chance to see the impaired pedestrian? Can parking and bus stops be managed to maximise sight lines? Can a refuge be constructed for the pedestrians to stage them across the road? Can crossing facilities be installed to assist the impaired pedestrian to cross the arterial road? There are 3 strategies available to you when providing for pedestrian safety: segregation, separation, integration. Segregates the pedestrian from the motor vehicle within the road network. At one end of the scale, this involves pedestrian malls, where motor vehicles are banned. And at the other end of the scale, it involves expressways, where pedestrians are banned. This category also includes pedestrian overpasses and underpasses. Separates the pedestrian from the motor vehicle, either in time by signals or in space by refuges. This is the most commonly used strategy by road safety engineers. Recognises that pedestrians and motor vehicles have to share the road. In these cases, the motor vehicle usually has the right of way. But good road safety engineering will maintain low vehicle speeds, good sight lines, and wide shoulders. However, especially in rural areas of Indonesia, helping pedestrians to integrate safely with motorised traffic is a worthwhile and positive strategy. Expressways. These high-speed, high-volume roads are designed to exclude pedestrians, ensure that minibuses are not permitted to stop along the expressway to pick up or set down passengers. Passengers are pedestrians once they are outside the bus, and they are at great risk if walking along or across an expressway. Pedestrian malls. Pedestrian malls are streets in commercial areas that have been modified for exclusive use by pedestrians. Traffic is excluded from pedestrian malls, or is permitted into the mall only with a special permit and under particular time, speed, and parking restrictions. Pedestrian overpasses. Pedestrian overpasses are not always popular with pedestrians. Many of them are steep and are slippery when wet. They attract stalls and hawkers who tend to restrict access. Because they are expensive to build, they tend to be big spacings between overpasses. Most pedestrians will not walk too far to an overpass unless they perceive the traffic volume and speed on the road to be very high. Pedestrian underpasses. Pedestrian underpasses suffer from similar problems to pedestrian overpasses. They also have one added issue. Many people fear for their personal safety when they have to use an underpass. Personal security is important, and some people, especially women, are afraid to use underpasses. This is more so at night. If an underpass is to be built, ensure that users can see through the underpass before entering, and ensure that it is very well lit at night. Intersection signals. Indonesia has many sets of intersection signals. Unfortunately, at most of these there are no pedestrian phases. no pedestrian lanterns, and no push buttons for the pedestrian to record their need to cross. Pedestrians instead have to navigate their way across these busy roads without any assistance. As they do not get the time separation they seek, many of them push their way into the heavy traffic. In doing this, they seriously disrupt the traffic flow and reduce the capacity of the intersection. They are at risk of being struck by motorcycles or cars that continue into the intersection at speed. This is inefficient, it is unsafe, and it is a sign that engineers responsible for the intersection have forgotten how to serve their largest group of customers, the pedestrian. Pedestrian-operated signals. There are a few sets of pedestrian-operated signals in Indonesia. These signals are effective at providing pedestrians with time separation in which to cross a busy road. You should consider installing pedestrian-operated signals across high-volume arterial roads within urban areas. They are not suitable for rural areas or for high-speed arterial roads where drivers do not expect to have to stop for pedestrians. They are also too expensive to use in the local street system, where vehicle volumes are usually low enough that safe gaps exist. A zebra crossing is a crossing that is marked with white bars, painted parallel to the direction of the traffic across the road, near which is displayed on each approach a regulatory pedestrian crossing sign. These crossings provide time separation for the pedestrians, but only if the drivers and riders respect the rules. While the road rules require drivers and riders to give way to pedestrians on these crossings, in Indonesia at present, they rarely do. You can assist pedestrians greatly by providing spatial separation for them. This means that they are given their own space within the road reserve on which they are able to stand, wait, and select a safe crossing time. One form of spatial separation is a pedestrian refuge. This is a small island located in the center of the road. It is designed to be conspicuous to approaching drivers and riders. It provides a space on which pedestrians may wait to complete their crossing of the road. The other type of spatial separation is a curb extension. These narrow the roadway so that the pedestrian walks a reduced distance to cross the road. With almost 40 million motorcycles currently on the roads of Indonesia, motorcycles now make up about 70% of all motorized vehicles in Indonesia. Tragically, they also represent some 70% of fatal road crashes. What can you do to improve safety for motorcyclists? The good thing to realize is that the road safety initiatives that you introduce for road users of cars, trucks, and buses will also greatly assist the safety of motorcyclists. By making sure you use good signs and delineation, using correct line marking, paying attention to roadside hazards, and by making sure that intersections are as safe as practical, you will be assisting all road users, including motorcyclists. But there are two things that you should focus on to help motorcyclists in particular. Seal the shoulders of your roads, and maintain your roads by keeping them free of potholes, sand, mud, and gravel. Bicyclists need three things for safe and efficient cycling. Space, a lateral space free of interference by faster and larger motor vehicles. Connectivity, a continuous route without squeeze points. Smooth riding surface, free of potholes, uncovered pits, sand, mud, and gravel. The term black spot evolved many years ago when police used black-covered pins to symbolize the locations of fatal road crashes on a wall-mounted map. In time, the worst crash locations became the blackest, and the term black spot was born. The term exists today to describe locations that have the highest number of fatal or injury crashes. The definition of how many crashes are needed for a site to become a black spot varies from one country to another. The black spot investigation process aims to develop a package of low-cost but high-benefit countermeasures that can be implemented at the site so that future crashes are reduced in number and in severity. Some suggestions for you to consider in developing a black spot definition for use in Indonesia are: make a list of all known safety problem sites on your roads. Count all known fatal crashes at each site in the past 3 years and give them 10 points each. Count all the serious casualty crashes at the site in the past 3 years and give them 5 points each. Count all the other known crashes at the black spot in the past 3 years and give them 1 point. Add up all the points. Repeat this for all the black spots that are known throughout your balai. Then, when you have done this for 30, 40, or even 50 sites, place all the sites in the same table from the highest number of points down to the lowest number. This is your crash location listing, and it is used to guide you to the sites that are most likely to benefit from black spot countermeasures. Engineers investigating a black spot do not look at an individual crash. Rather, they look at the patterns of the crashes at the black spot. While police investigate serious individual crashes, engineers look for patterns of crashes at a black spot in order to find these patterns and then develop cost-effective countermeasures to be funded. In order to identify your black spots, you need to work carefully down a simple, step-by-step process. Investigate all the black spot locations on your list. Starting at the highest point score sites first, work down the list, site by site, investigating each site in detail. Keep working down the list until all sites have been investigated. Obtain all crash data for the site. Obtain all the possible crash information for the first site on your list. To do this, firstly speak with the local traffic police and ask them for their records of crashes at the black spot. The traffic police have an important role to play in recording crash information. They are a crucial ally for road safety engineers because without good crash data, it is difficult to then develop cost-effective countermeasures for a black spot. Read the police crash data thoroughly and arrange it in a way that can assist you with the next step, the diagnosis of the crashes. Diagnose the crash problem. By inspecting the site, examining the crash data, and by examining the conditions at the site, a road safety engineer can make clear decisions about the likely source of the crash problem. Draw a crash diagram. A crash diagram is a sketch of the black spot that shows the direction that the vehicles or pedestrians were travelling at the time of the crash. The crash diagram is used to look for the patterns in the crashes. A crash diagram does not give any guidance with other patterns, such as the time of the crashes, or the weather conditions, or the people involved in the crashes. For those, we use a crash factor grid. Prepare a crash factor grid. A crash factor grid is a table that summarizes the known facts about each crash. Each column in the grid represents one crash. The rows represent factors such as time of day of week, weather, vehicle type, and crash type. Inspect the site. Armed with the information gained from the crash diagram and the crash factor grid, the investigation team then travels to the site and inspects it at the times that the crashes have been occurring. You should look with fresh eyes at the road environment. Ask questions. For example, is there something that may be misleading some road users at the site? Is the intersection conspicuous to all road users? Is the curve well delineated, or might some drivers or riders be surprised by its sharpness? Develop countermeasures. It is important to address the dominant crash patterns if possible, using the lowest cost countermeasures that is likely to be effective. Try to avoid expensive and complicated countermeasures. Prepare a design, estimate the countermeasure costs. Based on the package of countermeasures that are developed, prepare a draft design for the suggested countermeasures. Ensure that the design does not deviate from the intended package of countermeasures developed by the crash investigation team. Calculate the benefits and costs. When the design is complete, begin by calculating the cost, C, of your proposed countermeasures. Next, calculate the expected benefits, B, of your countermeasures. You get this from a set of crash reduction factors. Multiply the cost of the crash, CC, by the percentage crash reduction factor to obtain the likely benefits, B, for your countermeasure. Dividing the benefits, B, by the costs, C, yields the benefit-cost ratio, or BCR. The black spots that have the highest BCRs are the ones that should be funded first. Document the findings. Write your crash investigation report. Add photographs, all diagnosis tools, and draft designs. Send it to head office seeking funding for your countermeasures. Y-junction on a national highway. A busy Y-junction on a national highway. The highway is a two-lane, two-way road with some horizontal and vertical curves. Free travel speeds are generally 60 kilometers an hour. It is in a semi-rural area, however it is bordered by many houses. There is a downhill grade towards the Y-junction from the west. There is a sign to warn of the downgrade, but no warning of the junction and no line marking. Based on information from local traffic police officers, there is one serious crash per month. These crashes are mainly head-on crashes, trucks and buses from the east on the highway colliding with vehicles from the west, right turn against crashes, vehicles turning right at the Y-junction colliding with through highway traffic. Many of the crashes occur at night time. Replace the advanced direction signs on the western approach with 3 new reflective direction signs. Line mark the highway immediately west of the junction. Provide for a through lane in each direction, plus a right turn lane from the west to the south, the side road. Install 2 new streetlights at the junction. Black spot on a sharp bend on a bypass. The bypass is a part of a busy national highway. It is a 2-lane, 2-way road with a number of horizontal curves and several gentle hills. It is in a semi-rural area, but there are many businesses and houses starting to be built along it. It is heavily used by trucks and the pavement is in poor condition. There are large drop-offs from the road pavement to the shoulder. Based on local knowledge and police inputs, it appears that the crashes are a combination of truck rollover crashes, head-on crashes between trucks and buses with small vehicles, especially motorcyclists, a smaller problem involving run-off road crashes. Reconstruct this bend to provide for correct superelevation, coupled with wide sealed shoulders on both sides. Install a solid centre line through the bend for at least 50 metres on each approach to define the centre of the road and to prohibit overtaking here. Build up the unsealed shoulder around the outside of the bend. Black spot on a straight section of highway near a bridge. A new bridge was built a few years ago beside an existing bridge in a rural area. The highway was duplicated for a length of about 400 metres. The original highway is flat and straight. It was a 2-lane, 2-way road, but with a new bridge, it is now a 2-lane, 1-way road. Westbound traffic on the original highway now has 2 lanes in which to travel over the bridge. However, there are no signs or line markings to warn them of the return to the two-lane, two-way operation just over the bridge. Some vehicles in the right-hand lane have travelled directly into oncoming traffic. Based on local knowledge and police inputs, the crashes comprise head-on crashes between trucks and buses with small vehicles, especially motorcycles, at the eastern end of the duplicated section of highway. Reduce the westbound carriageway to one lane before the divided section of road ends. Use line marking and hatching to create a merge taper for the right-hand lane. Install at least 2 pairs of two-way traffic warning signs to face westbound drivers and riders. A curve on an urban arterial road. This recently duplicated bridge has 4 lanes in each direction. An exit loop on the departure side of the new bridge has been constructed to take the 2 left-hand lanes into a loop. However, these 2 lanes are trap lanes. There is no warning or information of this, and an old direction sign has been left in position from when the original bridge was 2-way. It is possible that this old direction sign has been misleading some drivers and riders on the new carriageway. Based on local knowledge and from police records of a recent multiple fatality crash, it has been concluded that these are run-off road crashes, mainly at night and mainly involving high-speed cars. Sideswipe crashes at the loop, mainly involving cars, motorcycles and buses. Install additional street lighting at the loop to highlight this location at night. Install a solid centre line through the loop to prohibit vehicles from changing lanes. Crossroad intersection in a small town on a national highway. This small intersection is a crossroad in a small town. It is an intersection between a small road and a national highway. Both roads are straight and flat. Traffic speeds on the highway are quite high, estimated to be up to 80 kilometers an hour when the traffic is able to flow freely. The intersection is in an urban area. The side road is almost totally inconspicuous from both highway approaches because of the buildings, an absence of adequate direction signing, a lack of warning signs, inadequate line markings, and no traffic control at the intersection. During peak times, 2 people carry out traffic control duties to help the side road traffic to exit. It is understood from local engineers and local residents that there are many crashes at this intersection, including right-angle crashes, pedestrian crashes, and some rear-end crashes. The most serious crashes occur at night, when volumes drop and highway speeds increase. Short term. Reinstate the centre line along the highway. Paint strong stop lines across the 2 side roads at the junction. Install at least 1 streetlight at the junction to highlight the junction after dark. Longer term, install traffic signals at this junction, ensuring the side roads are wide enough to accommodate 2 lanes of traffic. A road safety audit is a formal examination of an existing or future road or traffic project in which an independent, qualified team reports on the project's crash potential and safety performance. Road safety audit is a process of crash prevention. It aims to identify safety concerns in a road design so that changes can be made while they are still pencil lines on a piece of paper or a mouse click on a computer screen. By making changes at the design stage, safety can be built into the new road project, and the risk to the road users in the future will be minimised. Road safety audit is not simply a check that standards have been met. Rather, it is an assessment of how the future road users will use the road, and whether or not they may have some safety concerns with the new road. Road safety audits are most effective when undertaken at the planning and design stages of a new road project. As such, they are quite different in nature to black spot investigations. Black spot investigations are based on historical crash records. These records provide a view of the crash history at the site, and with an experienced team of crash investigators, low-cost crash countermeasures can be developed and implemented. The Road Safety Audit Team is the group of specialists that inject safety into the road design and assist the project manager to create a road that is as safe as reasonably practical. Road safety audit raises the issues of safety associated with the project to the same or higher level as other competing issues. There are 6 recognised stages at which a road safety audit is carried out. Planning stage. By providing a specific safety input at the planning stage of a road scheme, road safety audit can influence fundamental issues such as route choice, standards, impact on and continuity with existing and adjacent networks, and intersection or interchange provision. Preliminary design stage. Carried out on completion of the preliminary road design, an audit will examine typical issues including horizontal and vertical alignment, cross-sections, and intersection layouts. Detailed design stage. This audit stage occurs on completion of the detailed road design, but before the preparation of contract documents. Typical considerations include geometric layout, line markings, signals, lighting, signing, intersection details, clearance to roadside objects, and provision for vulnerable road users. Roadworks stage. This stage of audit includes an examination of the safety of the traffic management plans for the various phases of construction for large road projects, and it examines road safety at the roadworks site during the construction period. Typical issues to be examined include signs and markings, safe speed limits, temporary crash barriers, lighting, pedestrian routes, and driver appreciation of the correct path. Pre-opening stage. This audit involves a detailed inspection of the new road project prior to its opening. The new road is driven, ridden, and walked by the audit team to ensure that the safety needs of all road users are provided for. A nighttime inspection is particularly important to check signing, delineation, lighting, and other nighttime or low light related issues. Audits of existing roads. These audits aim to ensure that the safety features of a road are compatible with the functional classification of the road and to identify any features that may develop over time into a safety concern. Many of the safety concerns found in this stage of the audit should be readily addressed through simple and low-cost maintenance practices. There are 8 main steps in conducting a road safety audit. Select the road safety audit team. The road safety audit should be performed by a team of 2 or 3 people who are sufficiently experienced in the areas of road safety engineering, crash investigation and prevention, traffic engineering, and road design. Provide the team with the necessary background information. The project manager should provide the road safety audit team with a comprehensive set of drawings, plus any relevant reports and associated background information, so that the team can gain a good understanding of the project, its key objectives, and any associated issues. Hold the commencement meeting, if necessary. This meeting is arranged by the project manager and is intended to introduce the road safety audit team to the project manager, clarify any uncertainties either party may have about the road safety audit process, make arrangements for the site inspections to take place, provide an opportunity for handing over the plans and other background information, reach agreement on a timetable for the audit. Commencement meetings usually become less necessary as the audit process becomes more established. In time, most audits are initiated by email contact between the project manager and a selected senior auditor. Assess the documents and inspect the site. The road safety audit team then carries out the audit, generally starting with a desktop evaluation of all of the material provided by the project manager. Then, the audit team must inspect the site during both daytime and nighttime. The site inspection is essential for the team to gain a complete idea of the environment in which the project is located. It allows the road safety audit team to see how the proposal interacts with its surroundings and nearby roads, including sections of existing road immediately either side of the site. Write the road safety audit report. A road safety audit report includes the following information: a brief description of the project and its background, a list of the background information provided to the audit team during the commencement meeting, a list of the members of the audit team, details of when the audit was carried out, including times and dates of site visits, a list of potential safety problems identified by the audit team, including a brief explanation of each safety concern, an indication of the estimated risk. High, medium, or low are often used to indicate risk associated with each safety concern. Photographs of safety concerns. A signed and dated statement by the audit team leader on behalf of the team that they have completed the audit. Each safety concern reported in the road safety audit report will have a recommendation for action. The recommendation for each safety concern should be as clear and positive as possible. However, not all recommendations need to be detailed, especially if there are a number of possible options, or if there are so many competing issues that a considerable amount of redesign may be needed. Hold a completion meeting, if necessary. The completion meeting provides an opportunity to discuss the audit report findings, especially the recommendations for corrective action. In time, as experience grows with road safety audits, you may find the need for completion meetings diminish. Emails and telephone calls can provide all the necessary interaction that is required. Write the response report. The project manager is required to respond to each individual safety concern with a statement on whether the safety concern is agreed or not, and what action is to take place. This step is often overlooked in the road safety audit process, but without a written response report, there is a chance that the project team may overlook some safety issues later. Ensure the safety concerns are followed through. The project manager must follow through from the response report and ensure that the agreed changes are made to the project to accurately reflect the agreed improvements detailed in the audit report. Road and traffic engineers have always been concerned for safety and have always designed with safety in mind. However, many new road projects have opened and have immediately become black spots. Looking at how and why such projects slip through the traditional system of engineering design and checking yields a very positive answer to the question of why we need road safety audit. Road authorities are reminded that road safety audit is a more effective process if carried out early in the road design process. Therefore, you should maintain a focus on design stage audits. However, a safety audit of an existing road allows the identification of features that we know to be hazardous across the network, the identification and treatment of other potential crashes at a site that already has a crash record, there are some important things to remember when appointing an audit team. Always use a road safety audit team, 2 or 3 people, never a one-person team. Ensure that every member of the team is independent of both the design and the project. Select a senior road safety auditor who is experienced and knowledgeable about road safety matters for that particular stage of audit. The senior road safety auditor should be an experienced professional. The audit team can comprise members with varying lengths of experience. This mix of experience can be useful in assessing potential safety issues. Invariably, One or more engineers will be needed for design stage audits because of the need to examine many plans and the need to be able to think in 3 dimensions. Several nations have adopted nationally accepted accreditation models for auditors that are based closely on the following model that was initially developed for use by Austroads. 5 years minimum relevant experience in road design, traffic engineering, road safety engineering, or other road safety disciplines. Successful completion of a road safety training course approved and recognised by a national road authority. Participation in at least 5 road safety audits under the guidance or leadership of a senior auditor, of which at least 3 must be design stage audits, and another must be a pre-opening or existing road audit. Maintain experience by participating in at least 1 audit per year. The costs of conducting audits varies considerably and depends on the overall size of the project. However, in most cases, the cost of conducting an audit is less than about 2% of the design costs and less than about half of 1% of the total project costs. This is a small price to pay for improved safety. One of the most positive ways to ensure that road safety audit will become firmly established in a road authority is to establish a road safety audit policy. There is a need for all staff to be clear about what projects are to be audited and at what stages this should be done. These criteria are best detailed in a road safety audit policy. Such a policy will detail the types of road projects to be audited, the stage of audits that will be undertaken, and the reporting and responding system. The policy should be disseminated widely to all professionals in that agency, as well as to all professionals who have dealings with that agency on road-related matters. An example of a policy on road safety audit for an Indonesian road authority could be: all road projects in Indonesia will be road safety audited at the following stages, according to the class of the road, in accordance with the procedures contained in the Road Safety Audit Manual.